R square value. However, this R square, okay, there is a problem with this concept of R square. The problem is the R square statistic is somewhat problematic as a measure of the quality of the fit for a multiple regression model, because it always increases when a variable is added to a model. You can try this yourself, that if there is a model y equal to f x1 x2, right? You fit this model and you calculate the R square value, 0.41, let's say. If you bring some another slightly related variable or not related variable even, and you get a new model. The new model is y equal to f x1 x2 x3, and if you calculate R square value, it is possible that it may come out to be 0.48. It means you may think that R square is increasing, so model is getting improved. No, it may be possible that this x3 does not make any sense. But even then R square will improve. Why it is improving? Because you are adding some kind of new term which is getting optimized such that error is reducing. So in some indirect way you are adding a parameter which is slightly reducing the error, even though it is not physically related. So it may give a wrong impression. Even if the parameter is not related, it may give a wrong impression. Okay, so that's why we need to find a measure of this fit which is independent of these kind of things. And how do we do that? For that, we bring a factor known as R square adjusted. R square adjusted for these kind of things. Adjusted for these kind of things. It can be difficult to judge whether this increase is telling us anything useful about the new regressor or not. So R square adjusted has been used and has been defined as, so the definition of R square was 1 minus SSE divided by SST. Okay, so R square adjusted is 1 minus SSE divided by n minus p whole divided by SST divided by n minus 1. What happens that, what is SSE? SSE was sum of square of errors. What are errors? EI, right? Error is EI, so summation EI square. Okay, now divide by n minus p. Divide by n minus p. What is this n minus p? P is the number of regression parameters. P is number of regressors. In this model, how many regressors are there? In this model, how many regressors are there? 2. In this model, how many regressors are there? 3. N means number of data set, right? Because you are summing on n. Summing on n. So when you divide with this thing is nothing but unbiased estimator of variance of the error term. n number of data points. You are doing regression, right? There are 100 data points and you are doing the regression. And P, how many these things are there. So this is basically degree of freedom, you can say. Right? So suppose if there are 100 data point and you are fitting first model. So here this will be 98. For second model this will be 97. Okay? So now what is happening? See, with increasing number of parameters, this is reducing. So this ratio will increase if SSE does not change or change very little. So then this ratio will increase. If this ratio will increase, R square adjusted will decrease. Will decrease, right? So what is happening, that if you are increasing the number of parameters, then this number will reduce if and only if there is significant reduction in the SSE, and only then R square adjusted will increase and will give you a good information. So for this case, it may happen that R square adjusted for this one may come out to be, let's say, 0.4, and for this model it may be possible that R square adjusted may come out to be 0.35. And from there you can conclude that this was a useless parameter. This is a better model if you do the adjusted R square. Okay. But this analysis is useful only when you have options, whether to use this or to use that. But if you are very much clear in your mind that we know only this parameter is there, that there is no other second option, then you can use R square. Then you can use R square, because question of R square adjusted will come in the picture only when there is a P. P is changing, right? If only R square is there, then only thing that is coming in the picture is N. So if there is a huge N, right? If there is a huge N, then that R square will give you the correct idea about your fit. If N is small, then again the idea behind R square may not be very correct. So, okay. So this will increase only when a new parameter reduces the standard deviation of the error term significantly. So this we got about the R square adjusted. Now we can open the MATLAB code. So I'm going to close this because now there is no more slides. So in the last class we completed regression analysis, this code, right? Some more codes have been uploaded on the Moodle now. Okay, so in the coming days we will discuss this. Duplicate na. Okay, now you see. So till where we discussed this thing, analysis of variance. So did we discuss this ANOVA? No, na? We discussed till here, right? Okay, so first I will run till here, return. So I'm closing this. Now I'm going to run this section, analysis of variance. In the last class we discussed about the p-value. Okay, that's what we discussed, right? Where we stopped? P value. We stopped at the P value. Now I run this section. This is analysis of variance, ANOVA. What is this? Let us see. So yesterday, okay. So R squared we discussed. Here R squared is very poor. Now adjusted R squared 0.234. Here it is not showing much difference, and it is because here we don't have any option, right? We have only one model. So here both of them are not making any sense. The first thing is that the quality of it is not very good. Why? Because we know that it looks like a non-linear pattern, but still we have fitted a linear pattern. So it is very clearly conveying us your model is not good, because on a non-linear data you are fitting a linear interpolation. That's why R square value is very small, and R square adjusted is just adjusting for the number of parameters. How many parameters we have? Regressors. Only one regressor is there. So that's what it is doing. Correct? Now, there is a term, this F statistic versus constant model 60.6. This is something very important. This is something very important. F statistic versus constant model. Constant model, it is trying to say that there is no pattern. It is trying to say that there is no pattern. You can take a constant value of the model. Means you just take the data, you take the average, all of them, simply. Don't put any model, just take the average value. Suppose you are taking a C value, cohesion value, measuring on this mountain, right, from top to bottom. Okay, and with height, with depth, you plot the pattern between C and depth. There can be two options. You take the average of all C and define, okay, this is the average C for this entire mountain. So that will be considered as a constant C model, constant model, right? Another thing can be, you look at the pattern, that how C is varying with depth, and then you propose a model, regression model. That can be another thing. So whether you should make a model or you should take a constant value, that is told by this value, 60.6. This value should be as high as possible. This value should be as high as possible. Now, what is as high as? There is no guideline. But 60 can be considered as a high value, and at the same time, whether this 60 is meaningful or not, you can see from the p-value. P-value should be as small as possible. So what is the p-value? 10 to the power minus 3, 13.
That p-value is related to
only this statistic. Every statistic has one p-value. Chi-square statistic, T statistic, right? Similarly, there is a F statistic. The idea is not to learn what is F statistic, how it is calculated. The idea is, there is a statistic, but what it makes sense. What is the meaning of that statistic for an engineer, right? This value should be as high as possible. Second, p-value should be as low as possible. If p-value is higher, it means there is some problem with our F statistic. It is not reliable, as simple as that. It is not reliable. Either data is less or there is some serious mistake in the model analysis. These are the checks that these statistics tell you. Now we are coming to this part, which is ANOVA. You might have heard of this term ANOVA, analysis of variance. But what it is basically giving, it is giving nothing but whatever T statistic, F statistic that you calculate, all that in the tabular format it is giving you, without doing any calculations. That is the power of that analysis of variance. So first thing, if you see, so this column is sum of squares. This is degree of freedom. This is mean of square. This is F statistics. This is p-value. Okay. So total sum of square. This is, what is total? SST. SST. That's what we calculated here, right? So SST should be sum of model and residual. So check whether this number is summation of these two or not. Check. This number should be summation of this number and this number. So this is your squared error, SSE. And this is due to the regression. If you sum these two, you will get this one. Okay or not? Right? This is total degree of freedom. Similarly, this is the degree of freedom for the model. And summation of residual, and this becomes 195. Similarly, mean. So when you divide with degrees of freedom, this will give you the mean value because you are dividing number of data points, right? And F statistic is calculated. It has a certain formula with the using these values, and it is calculated. And p value comes out to be very less. It means this value is significant. It makes sense. It is not a nonsense because p value is very small. Okay. Similarly, there is a lack of fit. That how much there is a lack of fit. Now see. You know that we have fitted a linear model on a non-linear model. So lack of fit should be very significant. Now see, F value is very small. The value which should come from 60, 100 suddenly dropped to 0.45. And more important, this P becomes C very high, 0.98. 0.98 is very high. It means there is a very big problem. Why? Because there is a very strong lack of fit. We did it intentionally to demonstrate all these things. Because model was non-linear, but what we did? We forcefully fit a linear. It is shouting. These values are telling us there is a serious lack of fit. Okay. So these are some numbers which tell you a lot of things. More than the value, the meaning in the value is important. The idea is not that you calculate this statistic and put and get the marks. No. The meaning behind these numbers is more important. Now, we come to another command to solve the same problem. So there is another command which I have used here. So till now it was giving with all the details. Now we will get, so B is the regression parameter. What was the model? What was the model that we were fitting? What was the model that we were fitting? Your gamma was? Or y is, let's say gamma is y. Plus? X, right? That was the model that we were trying to fit, okay? So here, what it is trying to write, that input variables is nothing but, if you write in the matrix format, this is into 1. This is into X, right? So basically, this matrix getting multiplied by alpha beta gives y. 1 cross 2, 2 cross 1. Correct? That's what it is giving. That is the basic philosophy, that is the basic formulation of linear regression that we have studied, which I have not discussed here because that was not the point, right? So this is doing the same thing, and here it is giving 4 things. First thing is B. B contains the parameters alpha, beta, right? Because these parameters are coming from some data, so these are the estimates, so we will put a hat. Then second thing is B int. B int is nothing but the confidence interval, because these parameters are also random. Because if you change the data, suppose if you have 100 data points, if you select 10 data points, you will get some alpha beta. You select another 10 points, there will be another alpha beta. So alpha beta becomes a random number which will follow a distribution. So there should be a confidence interval, 95% confidence interval on these also. So B int gives you that 95% confidence interval on alpha and beta. If this interval is very small, it means your parameters are very precise. If this interval is very large, it means parameters are not precise. If your model is good, usually your parameter will be precise. If your model is not good, usually parameters will not be precise. The range will be big. Okay. Now this R is nothing but residuals. R is residual. What is residual? EI with sign. With sign. And again R int, interval of residuals, because residual itself is a random number, because alpha beta is a random number. So yi hat is a random number, so yi minus yi hat is a random number. So ri becomes a random number, so ri will also have a interval. So it gives the residual interval. We made one assumption, if you remember, everything is based on one single assumption, that your residual is always a zero mean process. Residual is a zero mean random process, correct? Random fields, I taught random field, remember? Zero mean stationary process, zero mean non-stationary process, right? Constant variance. Constant variance means stationary. Constant variance means stationary, correct? So what it is trying to tell, that your good model, a model that has fitted well without any bias. If there is a bias, it means residual is going to be non-zero mean. That was the case of model uncertainty, you remember? In the case of model uncertainty, we used to calculate certain bias in your model. Their residuals are not zero mean. But if you are fitting a regression model without any bias, your residual should be zero mean process with normal distribution. आधे इधर जाओ, बाकी मेरे पीछे आओ. Something like that. Okay. So now I am going to run this section. See, what were the, when we did that analysis, did you note down? So now my suggestion is, please note down all these numbers, because I may need them again and again. What was alpha beta we got? Shiva, can you, I forgot to bring the water bottle. What was the alpha beta? 9698. And beta? Minus? 0.0536. So see, first you are getting alpha and beta. Okay, now see the B int. So range, what is the 95% confidence interval on alpha? 2.53 and 3.0. Okay, so this is the 95% confidence interval on alpha, for which we got this mean value, this alpha hat. So this value is lying in this range or not? Similarly, this beta 0.036, what is the range of beta for 95% confidence? So it is lying in this range or not? Okay. Now let us visualize the regression fit. I am going to run this section. See. So with alpha beta, this alpha beta mean value, I have plotted my regression model, which is this, and this is the data. This is the data, original data. And we got this thing. So you can see the model is not very good. It is not able to capture this part, right? But this part is, you can consider okay, but it's even not that good. Why? Because even slope is very flat. That's why this is coming out to be very small value, slope. If slope is small, it means the dependence is not very clear. That's why slope is coming out to very close to 0, right? So that's what we expected, because we forcefully fitted a linear model on a non-linear data. And why we fitted? Because we wanted to demonstrate. Now let us visualize the residuals. Residuals means EI. We want to visualize them. How do they look? So this plot comes. Are you able to see? Huh? No, but you have to see in your screen actually. See, there are some red color. See, this is 0. This is the 0 line. Why it is coming like that? It is a problem of that or problem of my laptop? Projector, not my laptop. So you can see this is a 0 line. And you can see how the distributions are, how these lines which are denoting that length of residual are for each data point, how it is lying on top and below with this 0 line. Okay, but some points, if you see, where is your laptop? Oh, okay. So here, if you see, there is some data points in red colored. So those are going above this line. It means for them the mean value is not 0, certainly, because 0 is not lying in the range. Correct? The 0 is not lying in the range in that red line. If you see that red line, can you see? So see, this is 0. This the circle that you see is basically 0. It is not lying. So 0 is not lying in this range. These points are basically, it convey two things. First thing, it means first of all your model is not good. Okay. Second thing, these can be possible outliers also. These can be possible outliers also. But we are not sure. It can be problem of your model also. Because as we have seen, in this particular data, there was no outlier. Outlier were not making sense in this particular data, right? Even if these are not outlier, that can be the deficiency of the, thank you. This can be deficiency of the model itself. Now let us visualize the normal probability plot. I will explain what is normal probability, okay? Now let us run this section. We got this curve. This is very powerful graph which very clearly tells whether your distribution of the data, whether it is normal or not. If your distribution of data is normal, this should follow this straight line. Okay, so here on x-axis this is residuals, okay, and this is cumulative probability, basically probability in log scale. Okay, so what is happening, if you can see these points are the actual data. So you can see this much part is okay, but towards the ends this is not normally distributed. It means your first assumption was wrong. First assumption was wrong because it is not satisfying on the entire range. But this usually it will not satisfy. Even if your model is very good, it will be never perfect. It will be never perfect. But the idea is as close as possible. If it is to this line, then it will be normally distributed. So our practice, our intention should be that there cannot be exact match, but if it is closer, then it is good for us, correct? And if the points are very far away, so these can be linked with the outliers, can be linked, or it is your model's problem. Your model is not fitting good in this region. You can analyze. So this is another way to visualize the residuals. Now visualize residuals after removing outliers. In this, till now I have not removed the outliers. All that I was doing on the complete data. Now let us remove the outliers. Let us see what happens. I run this section and I got this. Now see, suddenly the red plots became very high compared to the last one. It is conveying, it means it is not the problem of outlier. It means your model is not good. You are blaming to the outliers, but your model is not good actually. And once you remove the outlier, then your whole story, it means when you are removing the outlier, you are removing something very important from your model. As simple as that. You should not remove the outlier in this case. So outlier are sometimes very important and sometimes they should be removed. That will depend what type of data is there, what type of problem is there. Now, we know that the model is nonlinear. So now we are going to fit. So with this analysis, we understood linear will not work. So now we have to go for the nonlinear approach. What is nonlinear? So let us discuss this thing before I actually go to the code. What is nonlinear? There can be two types of nonlinearity, nonlinear models. One is linear type nonlinear model and one can be nonlinear type nonlinear model. Okay, let us see. Suppose your model is, this is linear. This is but here is a multiplication. This is a linear type of non-linear. This is, I did not study anything like that, means this term I am just telling, linear type non-linear. Why? It means effectively you can call it a new variable x4 and then it becomes x3 plus x4 effectively. Okay, now this linear model or non-linear model? This is non-linear model. Why? Parabola has come into the picture. Non-linear, right? Non-linear or not? It's a non-linear model.
We can substitute.
Yes. So this is non-linear if you take the original parameters. If you substitute with y1, then it becomes linear in y1. Correct? So it depends what is the definition of your input parameters. So your model in original parameters can be non-linear, but when transformed, it can be linear in the transformed parameters. Okay? Now, this linear or non-linear? Non-linear? Okay. Now, in transformed state it has become. So for this model, will you do linear regression or non-linear regression?
Depend on which one you are.
You will do linear regression. ln(y), your output variable will be ln(y). So you will do a linear regression on the y to do the non-linear regression. Now, now, no, but still I can put x1 square as a new variable, x4. We can do that. So again it is a linear, right? Now suppose if you have this kind of model and your regression parameter are beta 1 x1 x square, beta 2 x2 square and beta 3 x3, then now this is linear or non-linear? This is something non-linear. It may not be possible, or it may be possible. Okay. Second thing. So this is first aspect of non-linearity, that you can deal it in multiple ways. Okay. First aspect. Now second aspect. Now second aspect. Okay. How many linear models can you fit on this? Simple this data. How many linear models you can fit on that form of linear model? to?
Transform linear.
No, transform linear actually, no, I'm not transforming. In the original variable case, I'm talking. That part is there. That part is used only for getting the parameters, for solving the problem. But after solving the problem, ultimately it is a non-linear behavior. How, suppose if you want to fit the linear, how many linear forms you can fit on this? One. There is only one linear form. Is there any other linear form in this world? No. At least I don't know. Okay. Now, how many non-linear forms you can fit on this? As many as you can think. I'm not saying infinite, but as many as you can think. First think y equal to e raised to the power minus x. Second maybe y equal to, let's say someone want to fit the cos x. Another one can be x to the power, or say 2 to the power minus x. Just assuming, or x to the power minus 3, or maybe 3, whatever. Okay. Someone can say y equal to ln x into e की power minus x. Let's say. So there can be as many as 4 non-linear forms you can think of. The problem of linear was very simple. One model, that's it. But non-linear, he can propose another model, you can propose another model, you can propose another model. Then which model to take? For our data, which model to take? Okay, R square you also come, and let's say R square is coming for his model, which is very complicated. See, you can put useless kind of model, useless kind of input parameters, and R square value can be improved. Even R square adjusted can also be improved in case of nonlinear if you play with the function. Then how to choose the nonlinear model? See, linear model, there is no choice. Linear means linear. What is the choice? But when it comes to the non-linear, what non-linear form you should choose? With different non-linear models, you can make a useless non-linear model which will give a very low p-value. See, you can play with all the things just by doing mathematics. That can, if p-value can controlled, R square adjusted can be controlled, then residual can be controlled. It needs little out-of-box thinking. Any answer? It can be a possibility जो सबसे simple होगा, okay, but I can find even simpler. Piecewise linear कर दो. Do piecewise linear. On this part you fit here to here, you fit this, then here to here you fit this, then here to here you fit this. Piecewise linear. इससे simple क्या है? Linear का linear, simple का simple. Piecewise कर दो, 10 pieces बना दो. Right? How to find the nonlinear model form? hint, the answer is not going to come from any mathematical number or idea. Answer is not hidden there. Answer is somewhere else. No, that is again mathematical answer. ग्राफ देख के पता लगेगा, तो ग्राफ देख करके आई कैन थिंक ऑफ सो मेनी थिंग्स, राइट? दैट्स व्हाट इज द प्रॉब्लम. बट यू आर गोइंग क्लोजर. No, again mathematical answer. See, answer is not in maths. No, even intuition, you are reaching very close to the intuition, but intuition comes from where? Answer is in the physics. First you have to see, you want to fit the model between which two quantities. Okay? Then from your physical understanding of the phenomena, you have to understand how this should behave. How this should behave, right? And then you fit the appropriate model which exactly replicates the physics of the problem, and then for that model you bring the parameter from the regression, not just like any Tom, Dick and Harry kind of model. Okay, for example, very simple example, welding life, right? We discussed, we fitted an exponential distribution, right? So suppose that data, welding life data is given to you. So you know that if it is used minimum, then its life will be full. If it is used longer time, infinite time, its life should be less. So you can think of, if I fit an exponential model that follows that kind of physics, you will fit exponential, right? So when proposing the non-linear models, you have to side by side think of the physics of the problem. What is the physics of the problem? If I take my parameters, whether they are making sense or not, whether physics is clear or not, this is very important when proposing the non-linear models. Non-linear models are not proposed just like that. There is a lot of thought, not just by looking at the shape of the data. If data is behaving like that, why it is behaving like that? And how it will behave like when it is outside the range of the data collected, right? That's why machine learning models, what they are doing, they are just taking the data, fitting in the black box, getting a model and applying. Where is the physics? Where is the physics? Gone in the black box. Gone in the black box. What you did? Just put the data, machine learning model, machine learning model, deep learning model, data. But that has importance. That has importance when you have big data, less number of time, and no knowledge, in-depth knowledge. The problem itself may be very complicated, right? When you put mosambi in that juice na, and then you do like this, so side se wo nikalta hai na, juice aa jata. So juice is that machine learning model. That kachada, that is physics. That gives na correct. That is physics that we throw. So even if, even if you are working on the machine learning model, okay, don't throw that kachada. Use that for some खाद बनाने के लिए, उर्वरक बनाने के लिए, गाय को खिलाने के लिए, ओके। So here, now you have seen that data was going like this. So very easily you can fit a regression model on that, exponentially decaying. How it came exponentially decaying? There was a physics behind it, not just like that, okay. So what happened, that the x-axis was the duration of the earthquake, y-axis was a parameter. Based on that physics, we already knew it, that parameter should reduce with the duration of the earthquake. It should reduce, and it should reduce exponentially. That we also knew. Luckily the data came also that way, and we fitted that it should reduce exponentially. Only the regression model gave what? How fast it will reduce. That's it for the given data. But that data was collected from the 956 earthquakes occurred in the western United States. But if I take the same data in Australia, what will change? Only the regression parameters will change, but because we captured the physics, so the model will remain the same. That is the beauty of physics. But suppose if you have not captured the physics, what will happen? There cos theta will fit, here sin theta will fit. Physics? Okay. So now I am going to fitting the nonlinear regression model. Okay. Let us see. So when you do any nonlinear regression model, again the philosophy is the same. Maximum likelihood you calculate and you minimize it. Right? The same philosophy is used. Only thing is, when the problem is nonlinear, you cannot simply solve it using the derivative thing, as we do in the case of linear thing. Linear derivative is very easy. What happens in nonlinear cases? You need to do some kind of iterative process to optimize. Whenever you do iteration, there is always necessary that you feed some initial iteration points where you begin. Right? In any kind of optimization problem, it depends from where you start. For example, in the case of nonlinear problems, it may happen that you have a function like this. What is this function? This is the function which you want to optimize. So your optimization condition says dy by dx equal to 0. Here 1, 2, 3. 3 places dy by dx is equal to 0. If you feed your system a point which is here, your numerical algorithm will take you to this one and stop the iteration, because it achieves dy by dx equal to 0. If you choose the initial point here, the algorithm will not go here, it will go here. If you choose the point here, algorithm is not going to here, it will go here. So when the problem is very complicated like this, either you use very complicated optimization schemes like genetic algorithm, okay, meta heuristic algorithms, particle swarm optimization algorithms, biomimicry based algorithms, that is another Mahabharat optimization world. Or you use the simple gradient based approach, but then you have to be very careful about your initial point. In simple problems, gradient based algorithm will work. So here I have used simple case. So initial parameters, so the model that I have assumed here, if you see, this is defining the type of model. So if you see, reg para means regression parameter alpha. Then second thing is input parameter is your x, and then power, in power reg para 2, which is this, okay, like this, equal to output y. This kind of model is proposed. Alpha, beta are the two parameters for which I have given an initial value. So alpha initial value I have given 1, beta initial value I have given -1. Why -1? Because I know that it is going to decrease with x, so I have given -1. And that one cannot be 0, so I have given 1. So I started with 1 and -1 and did the nonlinear regression. Let us run this. Run the section. It is running. It gave this nonlinear regression model, reg para 1 alpha, x1 is your input x, and reg para 2 is beta. So reg para 1 is coming out to be 9.07, reg para this is coming out to be -0.65. okay, and if you see, p values are very small. It means these two parameters are significant. They are not any Tom, Dick and Harry type of parameters. Okay. Now there were 196 data, error degree of freedom 194, because the two parameters we have estimated, alpha and beta. RMS error is 1.34. Earlier RMS error was coming how much? Did you note down? When linear model was fitted? I have here 1.6, yes, 1.6. Now 1.34, slightly reduced, not much but slightly reduced. Okay, R squared 0.461, earlier 0.238, significantly improved. Okay, not very excellent but significantly improved. Then F statistic versus zero model 203 jumped, p value -48, right? It means this is a very close to the real model. What is real model? Nobody knows. Real model? Nobody knows. But the numbers are showing that this model is very close to the real model. So when you read these numbers, this will give you a feeling of a doctor. When you do your blood test every Tuesday, go to the doctor, some red color, white color, it will come, and doctor will read. So same is your status now. This is the pathology report of the regression model. This is a pathology report of the regression model. Now, this will give you the nonlinear regression parameter in the same way. So I am going to run this section. So again I will see what is the regression parameter, 9.0793 and -0.65, right, which is matching exactly. So here I am going to visualize the nonlinear regression fit. Okay, running this section. Now see. Now it is making more sense, right, compared to the earlier one, isn't it? It is making much sense. Still, it's not very good, but this is what we can do at best, right? Now let us see how the residuals behave. Let us see how the residuals behave in this case. Like this. It's still not very improved, but by looking at the so many parameters, right, so many other things, this model makes sense physically and mathematically. I'm not saying that I'm going to bring the heaven to the earth, right? Because after all, it is a regression model. After all, it is a regression model. So regression model is like some average chopper that you use in your kitchen, right? Amount of kachada is less because kachada is also inside there. Still you are mixing it, right? Still you are mixing it. Still the kachada is there, but that is inside. Physics is imbibed inside that. Not purely data crunching, but some physics is there. But still, if you are doing regression, it means somewhere you don't know the physics, exact physics. That's why you are compromising. Now you are relying on the data. You are not explaining the data, but you are explaining the trend of the data. Right? So this can, so if you take one single parameter that my residual is not good, so my model is not good, no. There are so many things which you have to look at. Your physics, your R square, adjusted R square, p-value, parameters taken, simplicity of the model, okay, accuracy required in your estimates, right? Outlier, no outlier. Based on that only you decide whether your regression model is good or not good, or what kind of regression model I should take, what kind of regression model should I not take. These decisions are made on so many things, not just like that. Okay? So now we completed this one. Okay? Now we are going to open the second code, that is multi-regression linear. ओके कितना लंबा कोड है, ज़्यादा लंबा कोड नहीं है. इसको मैं सोच रहा हूँ आज एक्सप्लेन कर ही दूँ, हैं? अभी कुछ है नहीं, तो कर देता हूँ. तो इसमें पहले बता दूँ कि now what we are going to do. So here again we are going to the same data set. So this data set we are going to use, where we have our distance from the point of explosion, and this is explosion yield, and this is height of burst, the height of explosion from the ground surface, and P0, maximum pressure induced by that particular explosion. So P0 is the dependent variable because it will depend upon where your explosion is happening and how big is the explosion. And independent variables are R, W, HOB. So now in this problem, till now in the last problem there was only one dependent variable and one independent variable on which we fitted linear model, and then we fitted non-linear model. We did the entire analysis, we understood the concepts. Okay, now in this problem there are how many models, how many input parameters? X1, X2, X3. Okay, in this problem. Now again there can be linear regression, there can be non-linear regression with multiple regressors. So we have to look at that problem also. So now let us start. So I am running this section. Okay. Now I'm loading the input data. So there is a file data2.xlx. Okay, I have given the data there. Now it is loading the data. You can write down that x1 is range. Please note down all these things because this will help you in understanding this entire process. x1 equal to range, x2 equal to yield, w, and x3 is equal to HOB. Please note down this thing. Okay, range means R. So I have collected all my input parameters in this particular matrix x1, x2, x3. This is my input matrix, and y output is peak over pressure. Okay, you can write y equal to P0, peak over pressure. So I'm going to run this section. So now the data is loaded. Okay. Now let us visualize the data. How did we visualize the data for single case? How did we visualize the data for single variable case? Scatter. Simple scatter. Here how will you visualize? This is a multi-dimensional data. See, if it is two variables x1, x2, you can put on this plane, and then y you can put here, so it will give a surface. But now here we have x1, x2, x3. So now we need to visualize fourth dimension. Now we need to visualize the fourth dimension because we are three-dimensional creature. So we cannot visualize the fourth dimension. We have to visualize the fourth dimension in the third dimension itself. Okay. So when there is a multi-variable problem, there is a completely different kind of aspect for you visualize the data. So this is this. So I'm not going into the nitty-gritty of the coding because that is not my purpose. My purpose is to explain you. So I'm going to run this section. So data is visualized like this. Now what is this telling? This is a very important figure. It is trying to tell P naught R W HOB. Again this is P naught R W HOB. P naught with P naught. So it has plotted the histogram of P naught. So whatever P naught data was there, how it is distributed, it is telling here P naught with P naught. Now P naught on the y-axis and here R on the x-axis, then it is plotting how P naught is varying just with R without looking at any other parameter. So you can see that P naught is decreasing with R, right? There is this kind of relationship. So one variable you visualized. Now let us see. P naught is what? Over pressure. R is what? Range. If blast is happening very far, pressure there will be low. If blast is happening here, so here pressure will be very high. So it is following that trend. That physics is followed, correct? Okay. Now this is what? W. This is P naught. By looking at this, what you can understand? Now this is very important. I am lucky, actually you are lucky that I could get this data set and it explained so many things for real life applications. I never imagined because I did not do this analysis in my paper. But it is explaining so many things. This you will face in your research. What you can, by looking at this, what you can tell about the data? Just this. X-axis is W, Y-axis is P naught.
Probability was low or high.
You are thinking very complicated. Think very simple. Simple thinking. Ready? Simple thinking.
same weight taken in highlight both ways. For same weight. Both lower and higher.
Yes. So this thing is clear. For same weight, there are some low pressure, high pressure also. What does this mean?
Effectiveness of this load.
No. This means that although your weight is constant, but other parameters are varying these points, which are taking P naught higher, P naught lower. So first thing is this. Second thing, if you see very carefully, weight has only these two lines, right? It means in the entire data set there are only two types of weights. One is this, one is this. There is a categorization of the weight. Data is not uniform. This data is only for two weight values, right? First thing is coming in the, okay? It means data for weight is not sufficient. It means it is going to create problem in proposing a model. Now this is P, this is HOB. Now look at this and tell. Again same type of data, only difference is there are more number of values of HOB, more number of value of HOB, but ultimately you are not able to decipher the trend. So one thing is very clear, that R is playing a very strong role in defining the relationship. W data is not sufficient to make conclusion. HOB data does not seem to make any. This much you can understand by just by looking at the data. We are in the process of developing a a multi-regression model. So I am taking you with the process. Now again, this is R, this is P naught. So this is going to be just a kind of mirror image of that with axis changed. So this we have explained. Now this is the distribution of R. So there is a very big distribution of R, you can see. These many R values have been covered in this data set, which is very rich, right? If you see, the distribution W is so poor. It is for only certain values of W. Not all data is covered. Now if you see, HOB data slightly focused here. This data is not there, right? Now, this again, these things are just axis changed, so no need to explain. So diagonals explained and this part explained. Now this part, if you see R and this is what? RW. So R and W are completely uncorrelated. किस ऊंचाई पे कितनी दूरी पे हम बम फोड़ रहे हैं और कौन सा बम फोड़ रहे हैं क्या फर्क पड़ता है, कोई मतलब नहीं है. So this does not make any sense, this also does not make any sense, because they are completely independent parameters. So these are of no use to us. Okay. Now let us do the correlation analysis. Provides a measure of linear relationship between x and y. R is the correct correlation coefficient matrix. Okay. So now I am going to run this section and I am going to check this. See. So when you are running the correlation, so it is just, you can just see from the graph. This was P naught, this was R, W, HOB. This is R. This is HOB. So this is correlation between what and what? So self correlation is always 1, okay, and this is symmetric matrix because correlation matrix, and this one is W. This is P naught and this is parameters. So we can see only this part, right? So this is positive correlation, this is positive, this is negative, but this is not making sense.
Correlation for P and R
is increasing, but it is not making sense. Correct? It should decrease, na? It should decrease, right? But at the same time, one thing if you notice, this is very small, also very close to 0, right? Here it is showing clear trend that it is. Here it is showing a no. I think we have some mistake here. What is this actually? Let us check. X is what? X1 is range. So it is correct, right? Okay. Anyways, but these correlations are not making much sense. The one reason that can be here, because all data is completely mixed because when R is varying, with R, HOB and W are also varying. You have not fixed them. So it is kind of a mixed data. So when you are doing a correlation analysis, sometimes, and at the same time, if you see the correlation values are also very small, it is saying that your linear relationship is not very strong. It is strongly indicating that there is a very strong non-linear relationship, correct, in all these cases. But here at least, in this case at least, you can say it is decreasing. But these are not making sense, and at the same time they are very close to 0, right? So in statistics it is always important that don't just become very happy by looking at these numbers. You have to always analyze the numbers very carefully by understanding the data. The understanding should run in parallel with the statistics. Okay. Now where I am? Okay. Now remove the outliers using the MAD approach. MAD approach, mean absolute deviation from the median. Okay. I am going to run the same analysis which I explained. Okay. Let us run this section. So I have run. Now visualize after removal of the outlier. I am going to visualize now. Now see. It means here outlier plays a very big role. Can you see? Suddenly earlier these data sets were looking very ugly, right? Isn't it? But now at least these parts are filled. Why suddenly 1, 2, 3 appeared? Actually these 3 were always present there, but some of the data was so dominating that it was not visible in the, right? Sometimes when some data is very large, the smaller data you cannot see in the graph, right? That was happening and we were making wrong conclusions. But now you can see the data is filled, and see suddenly, before there were only 2, now suddenly appeared 3, and all of them 3 are comparable. It means if you remove the outlier, you will find that there were 3 significant W values, ranges at least, right? And here this trend has also come, which is following decreasing trend. Earlier it was decreasing but very sharp, but now it is coming out to be some kind of trend. But still it is throwing light on the fact that still this has a very broad range, right? Broad scatter. Okay. So here, unlike the previous case, here removing outlier was a good strategy. Earlier I saw that removing outlier was not making sense, but here removing outlier seems to make sense. Seems to make sense. Now correlation analysis after outlier removal. Let us see. Run section. Now, at least one thing is very clearly seen. These values have significantly increased. This is showing a strong negative, quite close to 0.5. Although this is higher than 0.5, but still it is not coming out to be negative. It is not coming out to be negative. The possible reason may be, what seems to me, that it is still mixed with the data of HOB and other things. And there is a lot of repeated data also. Why there is a repeated data? Because if explosion is happening here, okay, I plot a circle around me. On those all locations, I am at the same distance, but the pressure here, suppose 108 kPa, but their pressure can be 1110 kPa. So it means there is a duplicity of the data, because we are not taking the theta into the account. We are taking only R, H and W. So it means same R, H and W, there can be different P0 values, right? So there is some kind of mixed data, because one parameter, one information we don't have. That is information of the theta. We don't have our limitation, right? So that information can also play a role sometimes. How I know this? Only when you know the physics of the problem. Why I am able to tell all these things? Why I did not choose a pure mathematical problem? I could have chosen a very nice, decent mathematical problem which fits, and you clap after that and you go. But I did not choose that. I chose a real engineering problem. Because real engineering problems, so when you learn all the concepts in the class, but when you apply, यार क्या पढ़ाया था, जो पढ़ाया कुछ भी काम नहीं आया, अब सब मुझे खुद ही सोचना पड़ेगा, correct? But here I am giving you the opportunity to face the real thing that is faced in the research. Okay? So now you got, but at least it has started making some sense that after removing the outlier, these values have increased. Although this value is decreased, but order of magnitude is 0.2, right? So, but this is 0.52. Something strong is there. This is minus point, very close to the 0.5. Some correlation has started happening. It means outlier removing was the right decision. Now, linear regression analysis, multiple variable case. Now I am going to fit the linear regression model. So when I am fitting the linear regression model, there is only one possibility. What is? Y equal to alpha 0 plus alpha 1 x1, alpha 2 x2, alpha 3. Only one possibility. I am going to fit that. So run section, it has fitted and it has given the information about the MDL. Now regression model 1 means this is intercept, coefficient of x1, coefficient of x2, coefficient of x3. If you see, first look at the p-value. This p-value is acceptable. This is acceptable. This is this one. X3 was what? HOB. Right? It means there is some problem with this parameter. Okay. Okay. You can keep taking notes that HOB not from p-value HOB is not acceptable. Basically, you are behaving like a doctor. You are diagnosing whether this person has developed a cancer or not, correct? You cannot just by taking the CBC and telling, okay, your hemoglobin is less by 0.5, you develop the cancer. No. You are doctors, right? You are doctors or not? So again, this value you can note down, you can keep taking notes. Okay, we are going to solve this problem together. Okay, and intercept is, if you see that intercept is very large and x1 is very small, then x2 is, so it means why this awkward kind of parameters are coming. Now there are two things. First, there is some problem with the model. This should ring a bell. When you see some parameters very large and some parameters very small, this should ring a bell. One thing can be your model is not good. Second thing, the parameters which are coming to be very small, it means those regressors can be useless regressors. Now, x1 is what? R. Value is minus 0.62. So first thing, it is coming out to be negative for the first time. It means now your model has started speaking the truth. Slowly, it is telling the physics that it should decrease. X3 component coming out to be negative. X2 coming out to be positive. X2 is what? Weight should come positive, because if weight is large, pressure is going to be high. It means one thing is now clear, that coefficient of R has to be negative, coefficient of W has to be positive, and coefficient of HOB should be negative, right? Now P0 alpha 0 plus alpha 1 R, alpha 2 W, alpha 3 HOB. Okay, let us study the physics of the problem. So by studying the physics, that that alpha 1 should be negative, alpha 2 should be, and alpha 3 should be negative. That was happening. Now, what is alpha 0? Alpha 0 is a regression parameter, intercept. Okay, you can call it residual also, but physically what it makes, does it make sense? Okay, let us see. Suppose R is equal to 0, मतलब बम जो है आकर के चिपक गया छाती से, तो फटेगा, but that will not lead to infinite pressure, very high but not infinite. Correct? Correct? HOB 0 कर दो, same thing, right? W भी 0 कर दो, then pressure 0 होना चाहिए. Let us put in the model. ये 0, ये 0, ये 0, then model becomes alpha 0. Alpha 0 should be physically. It means but it is coming out to be, why it is coming out to be very high? It should come 0. Your model is not linear. First indication. Second, it is coming out to be very high because it is trying to adjust the error in the model. Suppose if your machine is not working properly, right? Okay, so what will happen in this machine, your kachada is coming out too much and juice is coming out to this much. Okay, that's why this 791 is very high. Did you get my point? Second thing, very important, which as an engineer you should have focused. See the units. Range is in, yield in kiloton, HOB in kilometer, HOB in kilometer. So when there is a significant unit disparity, then these kind of things can also happen. Correct? So you should always play safe. See, you can work in kilometer unit, no problem, but then your parameters may behave like this. So it should not, means when it is ringing a bell, you should consider all the possibilities. Now, after outlier removal, linear regression analysis, multiple variable case. After outlier removal, I have discussed this.
No. Without outlier.
No, this is after outlier, na?
Without outlier.
Without which line? Acha, this line, na? Without outlier. Okay. Now, after outlier removal, let us see. Okay. Now see at the parameters. Earlier this was coming out to be. Now see, kachada reduced. Why? Because there were some oranges which were completely juiceless. They were only producing kachada. Those were the outliers, you removed it. Now you are brought very high quality kinu. Right? Kinu data. And kachada is already removed. So it has reduced. It means removing outlier was a good decision. Now x1, earlier x1 was
minus 0.62.
now minus point reduced. This one
Increase
earlier,
2.3.
this one
Minus 280.
earlier, but now because kachada has been removed, although still the number are not very good, but p value is there.
It is increased from previous.
See, increasing decreasing does not make much difference. You fail by one number or you fail by 10 number, you will be called fail. You will not say, okay, I am senior to you because I failed by 1 marks only. Listen to my terms because you failed by 10 marks, right? No, both of you failed. So it does not matter whether P is a little higher or lower. It is bad means bad. So that is coming because your model quality is not appropriate. Okay, but some part it is just saying you that you have to remove the outliers. Now RMS now coming 50.4 earlier 813. See, huge jump, huge jump. R squared 0.488 earlier, huge jump. F statistics see here 22.7 and with significant value. So now here F statistics increased. It is nothing but giving us the confidence that you have to remove the outliers. First. Second, model should be nonlinear. So see, we are going step by step. On such a huge and complicated data, we are going to fit a model in the end. So this is the journey of that. Are you liking the journey? If you get bored, you can look out of the window. Now, analysis of variance, same thing. We run the section and again we get here same kind of parameters, which I don't think no need to explain. Some same squared error and all of those things. Now regression parameters and residuals. So again now I am going to see the regression parameters, okay, and residuals in the same way. So I run the section and I get here B. So first, so I did this on the without outlier. So same parameters are coming, and B int is giving the range. Now see, these ranges are very big, isn't it? See, any range you check, if the range is very big, it means your model, there is some serious problem, because it means your parameter is not precise. Your parameter can be anything between 586 to 996. Are you joking? Are you kidding me? It means these are the things which help you to understand the data in the light of the physics. Visualize, let us visualize the regression fit. Now here comes the catch. How did you visualize the regression in the case of linear regression? You did the scatter and you again fitted the model and you checked. But here you cannot visualize the model itself because it is a 4-dimensional model. Then how will you visualize your regression fit? So how do? We instead of plotting y versus x, we plot y versus y estimated. Y versus y. If it is good, then it will come a 45-degree line. So visualize the regression fit. See, from which angle this is a line? No angle. This is a very bad fit. Correct? Because, and you can see, it is non-linear. It means there is a non-linear problem. Again, this is another way. Now, let us visualize the residuals in the same way. Wow. Have you seen these kind of graphs before? Earlier, in the linear case, this was coming out to be some kind of a pattern, at least. But this is now coming out to be completely weird kind of thing. Visualize normal probability plot again for the residuals, okay? If I run that, see, this is somewhat okay. Compared to what we did, this is at least, see, a long portion is coming out to be at least following a normal probability line. But even if it is following, the model is not good because so many other things are not good. Now visualize residuals after removing the outliers, okay? See, after removing the outliers, still there are some, it is showing some outliers which it will show because model is not good, but slightly improvement is there if you see in the trend, very marginal visually at least. Okay, I am going to plot this section. See, this is very strong curve. Till now you have not seen this good. It means outlier removing was a very nice decision. It was not a waste of time. Now visualize the regression fit after removing the outliers. Run section. Earlier it was following some kind of trend. Now it is not following any trend, but you can see the things are getting stacked at certain locations. Why this is happening?
Our data sets are different.
Duplicacy in the data set, because duplicacy, not duplicacy mathematically, but at different angles same R is coming. and because of that this problem is happening. Because of this problem is happening, right? There are multiple values of y for same x1, x2, x3.